A Rubik's Cube is kind of a complex thing. It's difficult to solve. I've only got one side. Why am I showing you a Rubik's Cube? Well, I think in a lot of ways, it reminds me of the mind. And it reminds me of the challenges in trying to figure out how the mind works. It's kind of like trying to solve a Rubik's Cube. A Rubik's Cube is a complex thing. It's very difficult to solve if you don't know how it works, if you don't have an algorithm that guides how to solve it. So that's what we're going to talk about today. We're going to talk about how we can analyze complex phenomena in a way that makes them understandable and accessible. How do we understand complex systems like the mind? So remember our mantra. Cognitive science is the interdisciplinary study of the mind as an information processor. And we know that the mind is a complex information processing system. The question is, how can we understand such a complex system? The mind seems almost irreducibly complex. Just so many moving parts. There's so much that it does. There's so much hidden under the surface. How can we ever hope to break it down and understand what it is and how it works in any kind of reasonable detail? We need some kind of roadmap here. We need some way of making sense of all of this. We might need some way of understanding complex systems in general. Our problem is that we can't understand how the mind works by tracking its smallest units. And we can't understand how the brain works by tracking its smallest units. So we could record when each neuron fires and where it sends its signal to and what happens afterwards, but that's not going to really tell us anything about how the mind works. Right? The properties of the system emerge from the interaction of all those parts. It's not a question of just getting enough detail. In fact, sometimes I think seeing more detail can ultimately just make the whole picture even more confusing. So just like tracking the electricity flowing through a computer, through all those logic gates and circuits, may not tell us how a computer works, because those parts are hierarchically organized, and the behavior that emerges is much more complex than what we can observe in terms of electricity flowing through one gate or another. And that's true for the brain and the mind too, right? Neurons are organized into circuits, which are organized into brain regions, which are organized into a whole. But there's another layer of this problem, which is even just understanding the physical side doesn't tell us everything we would not want to know about how it works. There are many layers. The mind is a complex information processing system. It performs processes, mental operations, right? Remember our new mantra, the mind is an information processor that performs computations over representations. So things like language and perception and decision-making, these are complex systems that are being computed in the mind, that are executed by the brain. And remember, we can think about this with a computer metaphor. We can think of the mind like computer software, and the brain maybe like the hardware. Just understanding the hardware is not enough to understand what the whole thing does. You can't explain to me how Minecraft works by just talking about motherboards and RAM. You have to, at some point, talk about the program itself. So understanding the mind is similar. We can understand the brain and how the brain works, and that's helpful. We also need to know how the programming of the mind works. Beyond that, we need to also understand what computations the brain is undertaking. So there are several distinct levels at which we want to think about these kinds of complex systems. The neuroscientist David Marr gave us a system for describing complex systems at these different levels. David Marr was a vision neuroscientist who died tragically young, but left a very big impression on the field, on neuroscience and on cognitive science. David Marr says, if one hopes to achieve a full understanding of a system as complicated as a nervous system, a developing embryo, a set of metabolic pathways, a bottle of gas, or even a large computer program, then one must be prepared to contemplate different kinds of explanations at different levels that are linked, at least in principle, into a cohesive whole, even if linking the levels in complete detail is impractical. David Marr said that in his book Vision, which he wrote in 1982. And it really has been very influential for how cognitive science has evolved as a field. We think this is very foundational in terms of how we think about computation, how we think about cognition. So we can describe complex systems, really any kind of complex system. David Marr says we can describe any kind of complex system with these levels, including things even like a bottle of gas, a computer program, an embryo, anything. So of course this also applies to the mind and mental activity. Right? There's a physical level where processes are physically happening. There's a more abstract level where we can describe what those processes are in algorithmic terms, right? Talking about steps, sequences of operations. That's also where we will specify mental representations. Because remember, computations over mental representations. All of the mental activity that we're going to talk about is going to be defined in terms of computations over mental representations. And there's an even more abstract level where we can describe what the goals of the process are. And we'll talk about those in more detail. David Marr defined 3 levels at which we could describe complex systems. The highest, the most abstract, he called the computational level. And that's where you outline the goal of the system. What is the goal of the system? What is the goal of the computation? Another way of framing this for our purposes might be, what is the output of the computation? What is the object that will be computed? If you're going to do some kind of computation, it's really helpful to know what you're expecting to come out of that computation. What is the goal? What is the end state of the computation? Then we can talk about how we get there. That would be the next level of explanation, the algorithmic level. What steps are taken to accomplish that goal? What steps do you take to get to that output state? Also, what form of representation will you choose to perform operations on? The lowest level, the implementational level, that's where we describe the physical system that executes the steps specified by the algorithm. So while the algorithms specify the process that gets you to the output of the computation, the implementational level is also describing a kind of process, but it's a physical process. So implementational algorithmic levels are different in the sense that they are describing processes at sort of different levels of abstraction. The algorithmic level gives us an algorithm. It gives us a series of steps in language that we can understand. Whereas the implementational level tells us how those steps are physically executed in a physical system. We can take the Rubik's Cube as an example. The Rubik's Cube has a very clear goal. You want each face to have only a single color. So I've managed to get the white face, and I've got little bits of each of the others, but nothing very significant, so I'm only really about 1/3 of the way done. I guess I'm not very good at this. Solving Rubik's Cube is very hard, even if you know what the goal is. I know what the goal of the Rubik's Cube is. I know I need to get all of the colors onto each of these sides, but I don't know what the algorithm is. Without having that algorithm, it's very difficult to solve the Rubik's Cube. So we can describe the computational level of the Rubik's Cube in terms of the goal, the output state, right? The output state of all of the computations I will perform with respect to the Rubik's Cube is that configuration where one color, one side. Each side has a unique color. That's the output state for the Rubik's Cube. Okay, how do I get to that output state? That's where I'll define my algorithm. What's my algorithm for solving the Rubik's Cube? If you look online, there are lots of resources for solving Rubik's Cubes, and there are lots of algorithms that you could follow. They'll give you very specific steps about how to rotate in what order. Clearly, I have not followed them because I have not actually accomplished this. And then, of course, there's that implementational level. How do you actually execute those steps? Well, I have a physical Rubik's Cube, and I'm manipulating it with my hands. We could also program a virtual Rubik's Cube into a computer and maybe have an AI solve it. AI doesn't have any physical hands. It doesn't even have a physical Rubik's Cube. So there's more than one way to implement these algorithms physically, right? Different physical systems can converge on the same algorithms and the same goal. Let's take another example. Let's think about the game of chess. I like games, so I like talking about games. And I think that games are especially amenable to this kind of analysis. So you can think about a game like chess. Let's think about the computational level. What is the goal of chess? Or maybe what's the goal of a game of chess? I think a lot of you probably know it's something about checkmate, right? You want to get your opponent into checkmate. There's something about you have to have a special configuration where their king can't move without endangering itself. Something like that. Okay, well, that doesn't really make a lot of sense to me unless I know a lot of other stuff about chess, right? Checkmate, what's checkmate? King? I don't even know what a king is. How do you get things in configurations? How does any of this work? In order for that goal to make sense to me, I need to know a lot of other things, like what are the basic units in play here? You have pieces, your opponent also has pieces, they're on a board, you have different colors, each piece moves in a unique way. I have to know what captures are, I have to understand that pieces can be captured, they can't occupy the same space. So there's a whole theory of chess that I have to understand, even just to make sense of what the goal is, to make sense of that output state. And that's all description that's taking place at the computational level. Haven't yet talked about what an actual algorithm is to play or win a game of chess. So that will probably be my next question. It's like, okay, I know what my end state is going to be. How do I get there? Can you give me a series of steps that I can follow? Can you give me an algorithm that I can use that will get me reliably to that output state? That will let me win a game of chess? It's kind of a tall order, but yeah, maybe we can come up with some kind of algorithm that will help you win a game of chess. Maybe we can write a whole bunch of if-then statements. You know, if your opponent does this, then you should do that. Maybe I'll give you an opening move, and then, you know, your opponent will have a response, and here is a response you could give to their response, etc. Maybe you could make a big decision tree about all of the possible board states, and then you could chart a path through that decision tree. I think that's how some computer AIs actually do play chess. It'd be very difficult for a person because that decision tree is enormous. But there are multiple possible algorithms that you might choose that can help you play and win a game of chess. All of them are going to consist of some specific steps that you can take in order to play a game. Then of course there's that implementational level. How are you going to implement the game of chess physically, right? What will the game of chess physical implementation be? I can play the conventional way with wooden pieces on a wooden board. I can play with another human being. We're playing in real life, in meat space. That's the normal, conventional way to play chess. I could also play on a computer versus an AI or online against another person where there is no physical board. It's all just virtual space. Chess masters, people who are really good at chess, can also just play in their own heads. And they can play with each other without any physical board or even a virtual board. They're just playing completely inside their own minds by just calling out moves and then visualizing the board state in their head.
Bishop to queen 3.
Bishop to knight 5.
Knight to knight 5.
King rook to queen 1.
Queen to knight 4. Yeah, it's not even me. It's Morphy versus Anderson.
Pawn to queen rook 4.
Queen to king 7.
Queen takes queen.
Rook takes queen.
I'd like to talk about each of these levels in a little more detail. So we'll start with that computational level. It's sort of the highest and most abstract level. And this is where we give a precise formulation of the problem. What is the larger goal of the system in terms of some kind of process that will be completed? What will have been done? What will have been accomplished after the system has run its course, after you've completed your computation? Another way of thinking about that is what will be the output of the computation? If you can describe what the output of the computation is, and if you can understand what that computation means, if you can understand what the output means, what the significance of the output is, then you have a full computational level description. We can apply this to something like language and say, well, what's the goal of language? Well, there's a very broad goal of communication. Maybe we'll narrow it down a little bit. Let's suppose I just want to say a sentence. Well, that's my goal. My goal is to somehow generate a sentence, a valid string of words in the right order. That's how we might define what a sentence is at that computational level. I need to be able to produce a series of words in a specific order that doesn't violate any of the rules of English, let's say, since I'm currently speaking English. Okay, so we can describe what that output state looks like, and there are lots of little rules and things that we will have to obey. We'll talk about this more in the future about what exactly those rules are and what the output state of language really looks like. But there's going to be some rules that have to be obeyed. All of that is a computational level description. I don't know how I'm going to actually string the words together. I'm just describing what a sentence might look like and what kinds of constraints it would have to obey in order to be a good sentence. None of that says anything in particular about an algorithm or an implementation. Okay, what about the algorithmic level? Well, that's sort of the middle level of analysis. It's less abstract than the computational level, but significantly more abstract than the implementational level. And this is closer to how we think of process, the internal composition of a process rather than the output of the process, right? So we're thinking about the process itself, the thing that the mind actually does, step by step by step. How is the computation performed? How do we get to the output state? What is the form of the computation? But also, what kind of representation will we choose? There is a trade-off. Certain kinds of representations are very well suited for certain algorithms. On the other hand, certain algorithms are very well suited for certain kinds of representations. So the choices that we make may influence each other. The choice of algorithm may influence the choice of representation, and vice versa. And for any given computation, there might be multiple algorithms or multiple ways of accomplishing that same goal. So when we move down from the computational level to the implementational level, we're sort of creating a decision tree. Yes, there's one goal, there's one output, but there are many possible algorithms that we can use to get to that output. So for one example, we can think about how we add numbers in our heads, right? Take a number like 47 plus 21, two-digit numbers. How do we add it together in our heads? And you might get lots of different answers. I actually saw someone asking about this recently online, asking people, how do you add these numbers together in your head? And just keeping track of everyone's responses. It turns out we all have really different ways of going about this. So I could ask you, how do you add those two numbers together? I'll tell you how I add them together. I take 47, and then I add 20, and then I add 1. Somehow that makes sense to me. I don't know. 47 and 20 is 67, plus 1 is 68. You may have a very different way of doing it. You may take 40 and 20, and then 7 and 1, and then add those together. Or you may find some other way of doing it. There are lots of ways we might add these numbers together, and I saw lots of interesting responses about how people choose to do this. So for that one goal, we're all getting the same output, but we're getting there in very different ways. There are lots of different possible algorithms. The last level, the lowest level, the least abstract level, the implementational level. This is where we describe the physical system in which the process takes place. This is the physical system that executes the steps of the algorithm. So of course you've specified the goal of the system, the goal of the computation. There are many possible algorithms, but let's say we zero in on one. This is the sequence of steps we're going to take in order to reach that goal. Well, now there may be multiple choices for how we can physically execute those steps. At every point we're sort of branching into a sort of decision tree. And this is where we're going to engage with neuroscience in cognitive terms. We're going to engage with the brain. What's actually happening in the brain? What neurons are firing and in what order, and what do we think they're doing? How does that correspond to the algorithms that are being executed? This is where the role for neuroscience comes into cognitive science. One important point is that each of these levels can have unique types of models associated with it. Cognitive science, to a large degree, is a modeling science. We do a lot of modeling. Modeling is just a way of representing things from the outside world in a way that we can sort of understand. It's graspable. So we create models that describe how certain computations take place in the mind, how certain computations take place in the brain. And each of these levels that David Marr gives us may have some type of associated model that we can come up with that will describe things at that level. So at the computational level, that's where we're describing the output of the computation or the goal of the computation. And we might have some models that describe patterns of behavior, that describe the range of outputs that we can get for that kind of computation. Think of something like facial recognition. We know we can recognize human faces, but we're very bad at recognizing chimpanzee faces. So if we come up with a model of facial recognition, we have to explain that pattern of behaviors, that pattern of outputs. The fact that we have very good output for human faces and very bad output for non-human faces. At the algorithmic level, we have models that describe the processes that we use to achieve those outputs. So again, to think about facial recognition, we'd have to think of some kind of model that describes exactly what happens. Do we look at each feature of a face, the eyes, the nose, the mouth, and then bind those together? Or do we take it a holistic picture of all of the features all at once? Maybe we don't think of features at all. Maybe we match what we're seeing with something from our memory. There could be lots of possible algorithms to get to that output state. And then at the implementational level, we might have models that describe physical activity, right? The activity in the physical system. So what do we think is happening in the brain? What are these different brain regions contributing? How do different neural circuits interact with each other? So at every level, we have models that are describing something unique that contributes to the overall picture of how the whole system works. I want to make a quick note. I think it's important to draw a dividing line between algorithmic and implementational levels. I know these levels can be kind of vague or fuzzy or confusing, so I think it's important for us to delineate and separate the two levels in important ways. What I want to avoid us confusing the algorithmic version of how, right? We can talk about how things happen in the mind at the algorithmic level, how computations are carried out in sequence of steps. And I don't want to confuse that with the implementational how those steps are executed in the physical system, how those steps are carried out, right? The physical means by which those steps are carried out. When we ask how a computation is performed, it's sort of ambiguous. Do we mean how in the sense of the series of steps undertaken, in the software sense? Or do we mean how in the physical sense, the hardware sense? Okay, I know we've heard a lot of examples so far. I want to do one more example in some depth. I want to talk about a cash register. So let's talk about cash registers. What does a cash register do? What is the goal of the cash register? It's to add numbers together, right? You're at the grocery store, you want to check out, you put all the stuff on the conveyor belt, and the cash register is going to take all of the inputs, all of those values, the prices for all those items, and it's going to add them together to give you a total so you know how much money that you're supposed to pay. It's pretty straightforward, right? So the goal of the machine is to add. Well, that's not really enough for us to have a full picture of the computational level description. We need to know a little bit about addition and how addition works. What is addition? Well, addition is that thing we denote with a plus sign, and it involves mapping pairs of numbers into a single larger number, right? You take two quantities, you combine them to create a new quantity that's larger than either of the two. And addition has a few properties that are really important, right? Like commutativity. We know that adding 3 plus 4 is 7, and we know that adding 4 plus 3 is 7. It seems kind of obvious to us, like, oh yeah, you can put it in whatever order you want. The order doesn't matter. It's going to add up to the same number. Addition also has the property of associativity. So you can bracket 4 plus 5 and then add 3, or you can bracket 3 plus 4 and then add 5. Those will both also get you to the same value. It doesn't matter. It doesn't matter the order. It doesn't matter how you group them. Those are both important properties of addition that constitute part of the computational level theory of addition that's required for us to understand what the cash register is doing when it adds up all of the prices of the items that we're buying. Okay, well, how does it actually add those numbers together? How does that work? This is where we want to think about the type of representation that's in play. Cash registers use Arabic numerals, right? We use things like 1, 2, 3, 4, those symbols that we have, unique symbols for each number, 0 through 9, and then we use the place system. Turns out this is a really good system for adding numbers together. It's a really good system for multiplying and dividing. It's a really good system for arithmetic. So the algorithm that we have is going to have to make use of the fact that we're using Arabic numbers, right? So rules like adding the least significant digits, right? The things in the ones column and then the tens column and so on. And then carrying the 1 or whatever if the sum exceeds 9. So that's probably pretty familiar to us, right? Doing that kind of long addition. You add each column, you carry the 1, add the next column. That's what the cash register is doing. There may be other ways that it could do this, but I think that this is how it actually most electronic calculators work. Of course, we can imagine other kinds of representations, right? There's a representational trade-off. Arabic numerals are really nice for doing this kind of long addition. They're not as good at keeping track of the things that you have to tick off one at a time. So whenever you see an old cartoon with someone who's in prison, what are they doing? They're marking hatch marks on the wall, right?
Boy, am I glad to see you. I've been here 20 minutes already.
Well, that turns out to be a really good way of marking down values one at a time. If you were going to mark it down with Arabic numerals, you'd have to erase each one or scratch it out and write a new one, and then scratch that one out and write a new one. But when you're doing tallies, you can just keep adding one more mark. Tallies aren't very good for anything else. They're just good. That's really the only thing they're good at, is marking one thing at a time. Arabic numerals are good for addition and stuff. Roman numerals are not so good. If you guys have ever used Roman numerals, but it's kind of a wonder how the Romans got anything done. How were they able to engineer all that stuff with such a terrible number system? There's a huge trade-off here. Try doing long division with Roman numerals. It's almost impossible. It's a terrible number system if you want to do any real math. Here's a quick example of how the Romans used their numerals to do some pretty basic math. Romans only knew how to double and halve, so they had to do all of their calculations by doubling and halving. And they came up with some really interesting, kind of wacky algorithms to work around how impractical the number system is, by doing sequences of steps involving halves and doubles and then crossing out duplicates. It's pretty interesting, but it's not a very viable solution for doing the kind of math that we're used to doing, or the kind of math that a cash register is doing on a regular basis. So using Arabic numerals, or even like binary numerals, as long as you have that place system, these things are pretty easy to add and subtract and multiply, but Roman numerals are not. And the algorithms you have to use when you're using Roman numerals are very, very different than the algorithms that you can use when you're using Arabic numerals. So there's a very big trade-off. Okay, well, what about the lowest level, the implementational level for the cash register? Cash register is adding stuff together. It's following some kind of algorithm, probably adding least digits and carrying the one. Well, how is that actually physically executed? Well, a cash register is an electronic computer, right? It's got circuit boards, and it's carrying out the algorithm by sending electricity through logic gates, the same way that all computers do. So there's an implementational level explanation for how it's carrying out the steps of the algorithm. Remember that there are many possible algorithms to reach any particular goal. So for any particular computation, there may be lots of different ways that we can get to that computation, many different algorithms, many different sequences of steps that will get us to that goal. And there may be many possible models to describe the behavior of a complex system. And even once you choose an algorithm, there could be multiple types of representations that may work and may be available. Once you choose a representation and an algorithm, there may be multiple ways that you can physically implement that algorithm in a physical system. So at every level there may be new layers of choice. These levels of analysis are incredibly important for cognitive science. The mind and brain is such a complex system. It's not clear how we could ever have a full understanding of it without engaging with it at these different levels. I'll leave you with a quote by David Marr. David Marr once said, "Trying to understand perception," he was thinking specifically as a vision neuroscientist of perception, but it can apply equally to any of the other topics that we're going to talk about in this class. Marr says, "Trying to understand perception by studying only neurons is like trying to understand bird flight by studying only feathers. It just cannot be done." I think there's something very attractive about trying to understand complex systems by looking at their parts and how they interact with each other. But David Marr makes a really good case that that's not enough, at least not for us, to fully understand how that system works. We also need to think about goals, outputs, computations, algorithms. All of those things are extremely important for understanding how the system as a whole functions. All right, so some key concepts today. We talked about the mind as a complex computational system. We talked about how David Marr has these levels of analysis, or levels of description, or levels of explanation. The highest, most abstract level, the computational level. The next, the algorithmic level. The next, the implementational level. And we talked about representational trade-offs. How choosing one representational type over another may bias you towards one algorithm over another. And that there are lots of choices at each level. There are several choices for algorithms that can converge on a single computational goal. There may be several choices for implementations that converge on a single algorithm. And it gives us sort of a decision tree for explaining these kinds of complex phenomena.